Okay, let's do 2012, number 1. First of all, let's just orient ourselves to the problem a little bit. They give us a table of data. Notice that W of t is simply the function that gives you degrees. Okay, it's kind of like a displacement function. It's not a rate, it's just plain old degrees. So when time is 0, degrees are 55. Then when they give you the question, a couple things that you want to notice. They say strictly increasing. They usually don't give us much extra information. So strictly increasing is probably going to be important later. Twice differentiable, so maybe we're going to have to do some derivatives. WT is measured in degrees Fahrenheit and T in minutes, okay? Time equals 0, the temperature of the water is 55. Notice it already gives the initial condition in the chart, but they gave it again. So I'm wondering if I'm going to need that. Also, the water is heated for 30 minutes, but our chart only goes to 20. That's interesting too. And then it just reminds you that it's in the table above. So number 1 says, use the data in the table to estimate W prime of 12, etc. So you might first be thinking, well, how can I get W prime of 12? How can I get a derivative if I don't even have a function? And really, a derivative in this case would mean like, what's the rate of change? The instantaneous rate of change when time equals 12. And what you notice here is we don't know. In fact, we don't know any instant rates of change. We only know the temperature at certain times. To be honest, we have no idea what happens in between except that it's increasing. So the best we can do here is approximate it. And notice that they said estimate. So the closest thing you can do when you can't find a derivative and they ask for one is get the average rate of change. So let's get the average, the slope of the secant line between 9 and 15. Okay, so we know how to do that. F of B minus F of A over B minus A. In other words, if this were on a graph, we would just want to connect 9 and 15 and find out what the slope was. So we can run that, no problem. It's going to be W prime of 12 equals F of B minus F of A. So it's between 15 and 9, or 9 and 15. So it's W of 15 minus W of 9 over 15 minus 9. And why are we using the average rate of change of the secant line? Because we don't have the derivative, but they're asking for it, and they said we could estimate. So make sure you show this. Next step, you could just punch these numbers from the chart right into your calculator, or you could write the next step, which is just the plug-in, 67.9 minus 61.8 over 6. If you want to do dimensional analysis here, you can, but it's not necessary. Also, interestingly, a guy who graded the AP exams this year told me that you're allowed to leave the answer like this as long as you put units, because you really don't have to simplify an AP Calc. That creeps me out a little, and I'm going to have to explain my answers, so I'm going to go ahead and put it in my calculator. You should too. Don't forget to use parentheses in a numerator when you're using a calculator, and a denominator if it's more than one item. And you get an answer of 1.016 degrees Fahrenheit per minute, right? Because we want the rate of change. So what we just found was like the slope between these 2 points is 1.016. So that means we're going up 1.016 degrees every minute. That's the rate of change. Okay? Now we need to explain this answer. Oh, by the way, real quick, let's make sure it makes sense. Let's round a little. From 9 to 15, the temperature goes up like about 6 degrees. Is that about a degree a minute? Yeah, it is. 6 minutes, 6 degrees, that's what I got. So that works out. Now we have to explain this. So how do I explain my answer using correct units? Well, I think we've already been talking about it. This is the rate of change of the temperature of the water, approximately, at the 12-minute mark. So I think I'm going to make sure I kind of restate a couple things. W prime of 12, and that equals, I'm going to go ahead and say this again, even though it's right above. And there's my units. This is the approximate rate, or you could say estimated rate, that the temperature of the water, you shouldn't abbreviate, but I am, because I don't want to bore you. The temperature of the water in Fahrenheit, so let's mention our units again, is changing when T equals 12. I guess I'm going to say when time is at 12 minutes. Notice I said minutes, I said Fahrenheit. I stated the problem again that they wanted me to interpret. I said rate that the water is changing, so I got rate of change. Okay, and that would get you all your points. You get 1 point for this, and you get 1 point for the interpretation as long as you had the units in there. 2 easy points if you just knew the average rate of change formula, which you do know. So let's move on to letter B. Letter B wants to know to use the data, wants you to use the data to analyze, evaluate this integral. And wow, we don't have a function, so how can we evaluate an integral? Well, let's try it. W prime of t dt. Again, what they're really testing here is like, do you know what an integral is? And remember, I've told you a lot of times that if you have the integral of a rate, it measures the accumulation of whatever you're measuring. So we're measuring degrees, right? So if I put the rate of change inside an integral, this is the rate, I should get an accumulation of whatever I was measuring. Accumulation of measurement. So I was measuring degrees. So this answer should be how many degrees that the water changed, right? So, and it would be net degrees. Okay, so let's do this. Think of it this way. If this were velocity, we would be, let's say, miles per hour. This integral would give us how many miles we traveled. So if this is the rate that the water is heating up, this gives us the degrees that have changed. Okay, enough. Now, they really want to know, can you solve an integral without a function? And at first that's scary. You're like, how do I do this? Fundamental theorem of calculus. Remember this? Oh, here we go again. F of B minus F of A. Right? So let's do it. What's F of B? F of 20 is 71 minus F of A, which is, what is that? 55. And that should get us, what is that when you subtract it? 16 degrees. Okay, the other thing you could put here instead of F of B minus F of A, you could just put W of 20 minus W of 0. Same thing. Hey, 16 degrees, I got it. And then it said they want you to say, explain it, interpret the meaning of what does this mean. And I think I just talked about it. But it's going to be the total net change in temperature of the water from 0 to 20 minutes. So if you write that, you're in good shape. You can also say that the water was warmed by 16 degrees during that time. The temperature increased from 16 degrees over that time. And you're allowed to say increased because they already told us it was an increasing function. Okay, I'm not going to write that because I just said it all. Well, I'll read it though. The answer from the answer key says the water has warmed by 16 degrees over the interval from t equals 0 to t equals 20 minutes. Okay, you get 1 point just for finding this, and you get 1 point for making sure you have the interpretation with the units. Okay, not bad if you remembered the fundamental theorem of calculus. So let's move on. Letter C. Letter C wants us to find a left Riemann sum to figure out this integral. Okay, let's do it. So, but they also want average temperature. Okay, so average temperature, that's the average value of this function, is a formula that we know. It's 1 over B minus A, so that's 1 over 20. Evaluated from 0 to 20 will get us the average. Okay, so here we go. Let's just do this letter C. 0 to 20, I'm just going to go ahead and write it. W prime of t dt. And to do a Riemann sum, I need to do 1 over 20 because it's an average. Oh, don't forget that. And then a left Riemann sum means that we want rectangles here. And they said to use 4 subintervals, right? So And it says the 4 subintervals done by the table. Do you remember that I've told you to like build the rectangles on top of a table? I think it more helps you see what's going on. So now I can clearly see that there's a left endpoint here. And then this rectangle has a left endpoint here, left endpoint here, and this left endpoint is here. Okay, so there's my 4 left endpoints. And remember, a Riemann sum is the average of the rectangles. You also have to be really careful on these. They don't always have the same distance. So look, this rectangle is 4 units wide. This one's 5. This one's 6. This one's 5. So we're going to have to be really careful how we do this one. So it's going to be 1 over 20. The first rectangle is 4 units wide, and the left end of it is 55, right? So I'm just going to write W of 0 so that they know I know my left end. Then the next one is 5 units wide from 4 to 9. And the left side is W of 4. And then the next one, the left side is 9, but the interval, 4, 9. The interval is 6. Right, it's 6 units wide. And I'm going to use W of 9. And then the next one is, oops, I'm running out of room, 5, and it's W of 20. Okay, so this is just the area of each rectangle. And then again, you can show the next step if you want to write it out, or really you could just put it in your calculator. I'll write it out so you can see it's 4 times 55. That's the area of the first rectangle, 4 across, 55 tall. The next rectangle is 5 across, 57 tall. So 5 times 57.1. The next one is 6 across, and it's 61.8 tall. Sorry, I didn't show that very well. So 5, 61.8. And then the last one, I'm out of room again, is 5 units wide and 67.9. That was 6 units. I'm so sorry. This was 5 units wide and 67.9 tall. I hope you followed that. Sorry, I don't think I'm going to start over. We'll just go with it. And then when you put all that in your calculator, you get the answer, which is 60.79. Don't forget degrees Fahrenheit. And that's the average temperature. And then they want to know, is this an overestimate or an underestimate of the water? I'm like, oh yeah, wow. How does that work? I don't remember. So I know there's some rule, right, about left rectangles. So why don't you just sketch it really fast? Here's an increasing curve, and here are some left rectangles. Here's a left endpoint rectangle. Left endpoint. Look, these rectangles are all too small, aren't they? And then I'm like, wait, what about concavity? So let's try that. Left endpoint. Oops, still too small, isn't it? So if you have an increasing function and you're using a left endpoint, you have an underestimate. And really all you have to say is this answer is an underestimate because a left Riemann sum, I'm going to abbreviate a lot and maybe make it so you can see it. Because a left Riemann sum gives an underestimate when the function is increasing. And that was given, that the function was increasing. Okay, and again, if you don't have that memorized, it's just a quick sketch to get that, as long as you kind of remember that there was some rule. And I'm going to have to put the last one on the next recording.